Right now, I want to talk about scalars and vectors. Now, this is conceptual physics, and excuse the top of my head there, but I keep rolling over things. You can tell my office is immaculate. Scalars and vectors. This is a huge thing in physics. Now, you might be thinking, scalars? I've never heard of that. Am I going to learn something new? Well, probably you will, but this might not be the thing. It depends upon what your background is. Scalars, that's the type of math that you've been doing since kindergarten. Whenever you first started counting, you were dealing with scalars. Going through the grocery store with your mom or dad, and they say how many different kinds of soda there are, and you work on counting. 1, 2, 3. Those are scalars. Why? Well, let's contrast this. I have a can right here. It has a certain mass to it. If I turn it like this, it has a mass. Like this, it has a mass. Like that, it has a mass. I can take it to outer space. It has the same mass, although it might explode because it's pressurized. I take it to some planet which has an atmosphere. Take it to Mars, and it has a mass. Where it is makes absolutely no difference, and how it's oriented makes no difference. The number stays the same. That's one of the characteristics of scalars. Scalars don't care about direction, and that's a key thing. Scalars have what is known as magnitude, size, amount. Magnitude's the official physics term for it, but this is the kind of thing that we work with here. Scalars have been dealing with for a long time. Vectors, on the other hand, have direction. If I take this right here and I want to figure out its weight, well, the weight is basically the force acting down towards the center of the Earth. And you might be thinking, well, if I turn it upside down, the force is still acting down. Well, that's true. However, in this particular case, I could take it over to, actually, I could take it next door, and, well, the force of gravity is still downwards, but it's in a slightly different direction. Let's take an extreme. I go to the North Pole, and the force of gravity is here, assuming that get that oriented right, my head is the Earth. I go to the equator, and, well, it's pointing in that direction. The force of gravity acting on the object changes depending upon where it is, because the direction changes. That's what vectors are all about. So scalars don't care about direction at all. Vectors, we do. Now here's some, I'm going to start out with the easy one. Let's see if I can lift it just high enough to see just scalars there. Got my sophisticated graphics there. There we go, scalar. It would represent with a symbol. Get them backwards here. The symbol, you'd have just a single letter for the variable. Remember variables from math class? Yes, this is when you have to use them. There's nothing over top, and that'll become important in just a moment. And scalar math is the same kind of math you've been doing for a long time. 1 + 1 = 2. That's scalar math. Vectors. Vectors, we have the symbol over it. Right there. That means it's a vector. Now when you do vector math, direction matters, and so if I'm adding two vectors, both of length 1, now technically I know they're vectors because they have the vector symbol over it, but I don't know the direction. So I know when I add these together, I'm going to end up with a vector of anywhere from length 0 up to length 2. I need more information. So, vectors, direction matters. Scalars, direction does not matter at all.